Example. Find the area of the region enclosed by y equals 2x, the x-axis, x equals 0, x equals 4, by using a geometric argument. Okay, so I've included when I copy and pasted here, I've included the answers, but because they have nice little diagrams for us, but I will also go through it step by step. So here we have a diagram. Always helps to have a diagram. There's y equals 2x. Okay, so we're looking at that enclosed by the x-axis, which is here, enclosed by x equals 0, which is this line, and enclosed by x equals 4, which is this line. Okay, so we're looking at that yellow area there. So geometrically, we could say the area is 1/2 base times height because it's a triangle, and we know the dimensions of the base and the height. The base is 4, the height is 8, and so 32 times 1/2, 16 units squared. So showing that this new way also works, this definite integral, we're going to take the area from 0, is the integral from 0 to 4 of this function. Using proper notation, our 0 and 4 come out here on our square brackets. The integral 2x, add 1 to the exponent, so it becomes 2, and divide by 2. So that's just x squared. So 4 squared, subtract 0 squared, which is 16 units squared. Next example, find the area of the region enclosed by y equals x squared plus 1, the x-axis, x equals 1 and x equals 2. Okay, so again, a diagram helps. Here's the diagram, x squared plus 1, x-axis, x equals 1 and x equals 2. So we're looking for that pink area. Just using our integral then from 1 to 2 of this function dx, and that says 2 for squared. The integral then from 1 to 2. So this becomes x cubed over 3. This becomes an x, 1x. Okay, remember the same rule applies to a constant number when we're integrating it. The number 1 actually equals 1x to the power of 0 because x to the power of 0 is 1. And then if we integrate that, we would add 1 to the exponent and then divide by that number. That just equals x. It's just a reminder that a constant number, when we're integrating it, still follows that same polynomial rule. So here we have 2 cubed over 3 plus 2. Subtract 1 cubed over 3 plus 1. 8 over 3, the 2 becomes 6 over 3. Subtract 1 over 3, and the 1 becomes 3 over 3. So 14 over 3, subtract 4 over 3, which is 10 over 3, or 3 1/3 units squared. Okay, let's take a look at our graphing calculator. Get your graphing calculators out, please. Pause the video and get your graphing calculators out. 2 different ways on the graphing calculator. Okay, so from a graph point of view, we can enter our function, and the function was x squared plus 1. And there's our function. Okay. Now go to Menu, Analyze Graph. And we have this integral. Number 6 is an integral. So we're asked for the lower bound. We could move this around, but I will, and get it in the right place, perhaps, at a 1. I'm going to enter the number 1. Okay, so I know my lower bound is 1, and then enter that. Okay, it's asking for the other bound. Okay, so if I move this over here, it becomes an upper bound. So upper bound is 2, and enter. So this is pretty cool. It actually just gives us the answer, 3.33, which is the same as 10/3 or 3 1/3. Okay. Secondly, so let's go to home. We could do this from the calculator page also. Just using this button to the side of the 9, to the right-hand side of the 9. the special button here, and this integral. It's a definite integral. You can tell it's a definite integral because it has the little spaces for a and b to be. Okay, and just fill in the spaces. So from 1 to 2, and the function was x squared plus 1. And with respect to x, so dx, and then enter. And again, it gives us the answer right here, 3.33. So pretty cool. All right, so 10/10 is the answer there. Last example, find the area enclosed by the one arch of the curve y equals sine 2x. All right, so this is a good opportunity to review what we know about trig functions. Y equals sine y equals sine 2x. So if we're thinking of this, y equals a sine b x minus c plus d. That's the general formula for a trig function, sine function. A is the amplitude. Okay, so for this function then, the amplitude is 1. B helps tell us what the period is. Okay, so for this function, the equation is period equals 2 pi over b. And in this case, b is 2. So 2 pi over 2. So the period is pi. All right, and there's no other transformation. There's no horizontal transformation or a vertical translation. Okay, so we've got a period of pi. We can sketch this guy. This would be at 1. This would be -1 because that's the amplitude and no other transformations. Period of pi. So one whole wave all the way over to pi. We're looking at one arch of that above the x-axis. So we're looking from 0 to pi over 2. All right, so the area is the integral from 0 to pi over 2 of sine 2x dx. Taking the integral, put our boundaries over here. The integral of sine 2x. This is one of those ax plus b examples from section 18F in your textbook. So sine becomes negative cos 2x, but then we have to multiply by 1 over a, and in this case our a value is 2. So we have to multiply by 1 over a. So I'll put 1 over a here and move my negative sign further out. Oh, not 1 over a, 1 over 2, because a is 2 in this case. All right, so we have, I'll just rewrite this so we can see it. Now, never assume with trig functions when we're substituting in 0 that your answer for that is 0. Always do the substitution. So substitute in pi over 2 and subtract that from substituting in 0. Again, I'll do lots of steps as I always do. -1/2 cos pi. This will become a plus 1/2 cos 0. So cos pi on our unit circle. Pi is over here. Cos is the x coordinate, which is -1. Plus 1/2 cos 0. 0 is here on our unit circle, and that x coordinate is 1. So 1/2 plus 1/2, which is 1 unit squared. Okay, and back up to the top. Take a look. Yes, that's the same answer that we have in the book. All right, your homework for this section, section 19A. Please look at the homework document so you know what numbers to practice and have fun.